In this section, we're going to turn our attention upwards into the skies. We're going to look at heavenly bodies and circular orbits. So this title is the Circular Satellite Orbits. And a satellite isn't just the technology that we develop and throw up there. It's any object that moves around the central body is called a satellite. So between the Mayans, Galileo, Newton, they're all very interested in the skies and circular motion and the orbits of the planets, etc. So this is an interesting topic to look at as it affects planets, moons, comets and satellites. So these orbits can be taken to be circular. Technically they're not quite circular, but for our course we can simplify it down and the maths and the predictions work well at that approximation. Gravity is the force that holds these objects in place. So gravity keeps things moving in the circular orbit, so that means it's the centripetal force. Back to our Newton's laws. So Newton's laws of universal gravitation, that is always F is equal to G m1 m2 over d squared. So the force is the universal gravitational constant, the product of the masses over the square of the distance between them. In this section, because we're dealing with circular motion, then the centripetal force in question is F is equal to mv squared over r. So that's one of our key formulas from before. So the force we're dealing with in both cases is gravity, so we can make these things equal. So we can let this top one equal this bottom one. So we have this is equal to this. So we're trying to find a link between them. The mass here, that's the mass of the body as it is here. So we have capital M for the central mass, the mass of the large body, and small m for the mass of the small body. That would be the moon, that would be the satellite, that would be the comet, whatever is moving around in the circular path, and then that would be the central body and moves around big M. I'm using R instead of D. We could use either, and that's the distance to the body. So we have the masses cancel, one of the radiuses cancel, that's R squared, so they cancel, we're left with R. So our relationship ends up being B squared is equal to GM over R. So if we take a closer look at this formula, when we have a body that's moving around, that's going to have a fixed radius. So if we look at the moon, it moves around the earth in a fixed radius. The universal gravitational constant is always constant, and m being the mass of the earth, that's always constant too. So tick for a body like the moon, it's going to have a fixed v squared. You then get the square root of that, and that would give you v. So the only variables in this equation are velocity and radius. So even in a general case where you're not looking at a specific body like the moon, g cannot change, and if it's going around the earth, m cannot change. So if v changes, r has to change. If r changes, v has to change, because they're the only variables. We don't have mass or anything else for the body in there. So the distance, this is the distance from the center of the earth, and you might need to adjust this to be the height above the earth. So therefore the mass of the body is irrelevant. It's not, doesn't make any difference. So if you had a pea or a moon or a planet, it doesn't make any difference. It's the gravity, the mass of the central body, and then it's a relationship between radius and velocity. The period of an orbit then, when we start to look at this, so how long it takes to go around. So the time taken for a satellite to go around the central body once is called the period of the orbit. So again, if you have a satellite in space that's giving you GPS or something like that, the period of that satellite is given by this formula here. And likewise, you can take a comet like Halley's Comet, which goes around the Earth. It's got a very long orbit of something like 83 years. You can take any of the moons that go around any of the planets, and they'll all follow this formula. So the length of time it takes to do one lap, one orbit, capital T, is 2 pi r over v. So again, the only things that change here are r, v, and t, because 2 pi is a constant. As we move on, we have then to figure out the relationship between the period of an orbit and its radius. So we want to figure out radius and period, how they link between each other. So we got a rough diagram here. So this is your body that's moving around. This is your central body of mass capital M. Then we have a distance between the centers of the bodies, and I've called that capital R. And then it's got a linear velocity at v. So that would be the tangential speed, whatever we'd want to call it. Then we have the satellite, which has mass lowercase m. So we take this situation, and this is the central body, the heavier one, and then we have the circular orbit. The force that holds it in that orbit is gravity, and we have the smaller mass then of the second one. So this is looking at what we did previously in a bit more detail to bring it all together. So from Newton's law, we have this. So force is G capital M small m over r squared, and centripetal force then is F is equal to m p squared over r. We equate the two of these. We can cancel the m's like we did before, multiply both sides by r, so r will cancel with the squared, and then r and r will cancel to give you 1. So what you get left with is v squared is equal to gm over r. Then we will bring in our other formula. The period of the orbit, capital T, is equal to 2 pi r over v. So we square both sides then, because we're trying to get a relationship between the two of these things. So we square both sides and we get t squared, and we square the top line, so it's 2 by 2 to give you 4, pi by pi to give you pi squared, r by r to give you r squared, all over v squared, because we square top and bottom. So we now have this relationship here, so t squared is equal to this formula. But from up here we know that v squared is equal to gm over r. So we can do some substitution here. So we replace this v squared with gm over r, and that's why we squared both sides in the first place, to get that relationship. So we take a look at this. T squared is equal to this. We're dividing by a fraction. When you divide by a fraction, you can invert and multiply. So I've written it as 4 pi squared r squared over 1 multiplied by invert and multiply. So that's r over gm. So I've inverted it, flipped it, and multiplied. So what happens then is I get r by r squared, which gives me r cubed, and I get 4 pi squared r cubed over gm. So that is my formula. It's a bit more complicated, but again, when you look at it, it isn't that complicated, because 4 pi squared over g, that's a constant. So that's a figure no matter what. 4 is 4, pi is pi, and g is a universal gravitational constant, so that's fixed. So then all you're left with here is the period squared. That's going to be linked to r cubed. So the period squared is proportional to r cubed. That's a famous rule called Kepler's law. And Kepler was a physicist who came before Newton, and his laws were well established. So when Newton developed his idea of gravity, that gave a further explanation to Kepler's law, so it followed Kepler's law, so that gave it that extra rigor, so people found it much more believable because it explained Kepler's laws. When we look at this in more straightforward, we don't want t squared, we just get the square root of both sides, so t is proportional to the root of r cubed. So that's how they change. So if t doubles, the square root of r cubed would also double. If t halves, the period halves, the square root of the radius cubed would also have to halve. And the other thing that it's linked to then in general is the mass of the bigger body, so the mass of the heavier objects, such as the sun if you're looking at the solar system, or the earth, or whatever other planet you have a moon or something going around. And again, typically you might be looking at satellites that we have put into orbit, so man-made satellites, and then your central body is always going to be the mass of that central body, that central thing. So the period then is related to 1 over m, the square root of m. M is on the bottom, so it's 1 over m is the inverse relationship, and you get the square root of both sides, so you got these two here. This one, t squared, is proportional to r cubed. That's the most important one, because again, for a particular body, m will also be constant. Finally, what we're going to look at is a satellite stopped above the equator. So this is kind of an interesting topic. It's the kind of thing you'd need if you were spying on terrorist groups or things like that, or even just putting internet service into place or GPS signals. You need satellites which are fixed in certain spots. That means you're not going to get blackouts. If you had your satellite sitting over the Atlantic part of the year, or part of the day, should I say, or they were over the wrong part, you would have bad service and get interrupted. So what physicists and scientists and NASA and people like that have figured out is how to get satellites fixed in a particular place. So they will say sitting over the same point on the Earth all the year long, all the day long. So we'll look at this now. So the period of the Earth is 24 hours. That's one revolution. So that's what a day is. It's one spin of the Earth on its axis. So if a satellite has the same period and was above the Earth's equator, it would remain fixed above the central point on the equator. So what that means is, and again this goes back to one of our previous things, it would have to move quicker to keep up with the Earth. But if you had a satellite sitting, and again we talk about the equator, so if you were sitting above equator, you could sit above the same house if you were moving in the same direction and you had the same period. You went around one lap once. So you could be sitting above a particular point on the Earth's surface and you would remain fixed there. So if you were looking up, you could possibly see the satellite if it was flashing or something like that, and it would remain sitting above you all day long. So a satellite like this is said to be in a geostationary orbit. So geo is Earth, stationary means not moving, and orbit means going around, and that's commonly called a parking orbit. So most communication satellites are geostationary, and that's very useful because you want satellites to be in equal positions, so they will communicate with each other and bounce the signals around and send them back to where they need to be sent to. So for the planet Earth, a geostationary orbit above the equator happens at 4.24 by 10 to the 7 meters. That's away from the center of the Earth. and that will correspond to 36,000 kilometers above the Earth's surface. So in this situation, t is proportional to r only. So the period is only proportional to the radius. Technically, it's t squared is proportional to r squared, but those two things affect each other. To find other geostationary orbits at different latitudes, we would need the radius of the Earth at this latitude. So again, it's important, because this is a tricky thing, it's important that you understand the difference between the radius of the Earth and the radius of the orbit. So we're going to look at that in this diagram in a second. So the equator is focused on, and of course that's the easier case, because in that case both of the radiuses are equal. So if you take a look here, this will be your circular orbit at the equator, roughly a circle. So here, this slice, so again, the Earth is a sphere, we're looking at the kind of core, so taking a slice out of the middle, so that's the circle that we're looking at. So that's the radius of the Earth, and that is the radius of the planet at this latitude. Anywhere along will be the radius, but if we come down further, so we take a slice lower down or a slice higher up, that's going to have a smaller radius. The radius of the Earth is obviously still the same, but because we're dealing with this two-dimensional plane, it's going to have a different radius. We did look at that problem before of how to find that, and we need to make a right angle triangle, and we need to know the angle of latitude. So it's something we can do, but when we focus on these satellite orbits, we just stick typically above the equator, but it could be done at any radius. And again, as we've seen before, the period is only proportional to that, well, not the radius of the Earth, it's the radius to the satellite, but that's the only thing that matters. That height that you set it at will give it a certain speed, and that will give it a certain orbit, so you can have this parking orbit or this geostationary orbit. So again, you have this point on the Earth, on the sitting on the equator. You have a satellite that looks a bit like a Death Star, not a Death Star, that other ship that Darth Vader flies around in. That will be sitting above this point. So if this is fixed at a certain radius or a certain distance from the center of the Earth, then it will go a certain speed, and then it will keep that its period will be 2 pi, 1 full revolution in 24 hours, and then it will stay sitting above that spot there. So a geostationary orbit can only occur at a certain height, and that's because height, the distance from the center of the planet, the speed, and the period are all linked by the formula we just looked at. So this is how we can establish this geostationary orbit. This is our formula down here. T squared is equal to 4 pi squared r squared over gm. So the period squared, 4 pi squared over gm, that's constant for Earth, and then the radius squared, sorry, that should be the radius cubed, so I made a mistake there, but that's what the formula should be, and that all links together. So then, just to be fully precise, there's 3 conditions to get a geostationary orbit. The first one is the satellite orbits in the equatorial plane. So again, that means kind of directly above the equator. Its period is 24 hours, which when we're doing our calculations, we convert to seconds. So that's 86,400 seconds, 24 by 60 by 60. And then finally, the obvious one, the satellite moves in the same direction as the Earth rotates. So if the Earth is going clockwise, the satellite is going clockwise. The Earth goes counterclockwise, the satellite goes counterclockwise. So it's important that they move in the same direction. So there are 3 conditions for a geostationary orbit and the things that go with them. So the next thing to do is practice, and we'll get some questions to finish off our study of circular motion.